In this lesson, we will derive the equation for the velocity profile of fully developed laminar flows in pipes. Most flows in everyday life are turbulent, and often they are not fully developed. However, we can derive an exact expression of the velocity profile only for fully developed laminar flows, although there are approximate expressions available for fully developed turbulent flows as well. We begin the derivation by examining the forces on a small cylinder of fluid in a fully developed flow. In a previous video, we applied Newton's second law in the axial direction on a cylinder of fluid of radius lowercase r and length L, and found an expression relating the pressure drop delta P and shear stress tau. We can rewrite the mass m as density rho times the volume v, and the volume can be further rewritten as pi r squared times L. Rho and g can be combined into gamma, and the equation can be solved for tau. Since delta p, L, gamma, and phi are not functions of radius, this means that tau varies linearly with r. The shear stress is 0 at the center of the pipe and reaches a maximum value at the walls where the velocity gradients are largest. These conclusions are valid for both fully developed laminar flows and fully developed turbulent flows. So far, velocity does not appear in this equation yet, but we can relate the shear stress to velocity gradients in the flow. For fully developed laminar flows, the velocity vector only has an axial component, Vx, which only varies in the radial direction. For Newtonian fluids, we can relate the velocity to shear stress through the equation tau equals negative viscosity mu times the velocity gradient dvx dr. The negative sign appears because the velocity decreases in the radial direction, making the velocity gradient negative. However, tau must be a positive quantity. The negative sign accounts for this. Substitute this expression for tau into Newton's second law and solve for dvx. Now we will integrate both sides of the equation. Most of the terms on the right side of the equation are not functions of r and can be removed from the integral, leaving r dr. The integral of dvx is simply vx, and the integral of r dr is r squared over 2. We also must include a constant of integration, c. Let's move the equation to the top of the screen and bring the factor of 1/2 into the parentheses. To determine the constant, we must apply a boundary condition. At the walls, we have the no-slip boundary condition. When the radius is capital R, the velocity is 0. This allows us to solve for the constant c and plug this expression for c into the equation for Vx. Vx is equal to the quantity delta P over L minus gamma sine phi divided by 4 mu times capital R squared times the quantity 1 minus lowercase r squared over capital R squared. This equation describes a parabola. We can further simplify this equation by rewriting it in terms of the centerline velocity, Vc. This is the speed at the center of the pipe where the speed is the greatest. Plugging in 0 for the radius, lowercase r, and comparing the expression for Vc to the expression for Vx, we now have that the velocity profile is equal to Vc times the quantity 1 minus lowercase r squared divided by uppercase R squared. This means if you know the centerline speed, you can calculate the entire velocity profile. With knowledge of the velocity profile, you can calculate useful quantities such as the volumetric flow rate Q. Q is equal to Vx dA integrated over the entire cross-section. Since we are dealing with a circular pipe, we'll integrate from the center of the pipe, where the radius is 0, to the pipe surface, which is a distance capital R from the center. The small area dA is the area of a thin annular strip of thickness dr. This strip is a distance lowercase r from the center of the pipe. This means the area of the strip is a circumference 2 pi r times thickness dr. Plug in the expressions for Vx and dA into the integral, and remove 2 pi Vc out of the integral because they are constant. After evaluating the remaining integral, we have Vc over 2 times pi capital R squared. The volumetric flow rate Q is also equal to the average speed V average times the total cross-sectional area A, which is pi capital R squared. Comparing the two expressions for the volumetric flow rate, we see that the average speed is 1/2 the centerline speed. If we plug in the expression for the centerline speed into the volumetric flow rate equation and substitute d/2 for the pipe radius, we obtain a relationship between the volumetric flow rate, the pressure drop per length of pipe diameter, pipe orientation, and fluid properties. This equation is called Poiseuille's law. It is important to remember that this equation is only valid for fully developed laminar flows through circular pipes.